All right, so here you have exchange of dance partners, the Na and the SO4. Two NAs, you need a coefficient of 2, so Na2SO4. And then this is going to combine with the HCO3, all right? So it is going to be, so if you have a coefficient of 2, right, it's going to be 2HCO3, all right? So that means you're going to get 2 waters and 2 CO2s, okay? All right, Na and the Br will combine. You need 2 here coefficient. So you get 2 NaBr, and if there's 2 H's, it combines forming H2CO3, which breaks up into H2O and CO2. Okay, so here you have 2 Ks, so you need a 2 here. So that's 2 KCl. And then again, if you have a 2 here, H2CO3, which gives you H2O and CO2. This K and the NO3 combined, KNO3, and this H and this HCO3 combined to give you H2O and CO2. Mg will push out the hydrogen, giving you MgNO3, and make sure to have a 2 here so that you get H2. Okay. MgNO3 2, okay, because NO3 is 1 negative. Ag will push out the hydrogen, make sure to have a 2 here so that you can get H2. So 2Ag plus 2HCl gives you 2AgCl plus H2. Na will push out the hydrogen, so you get, and also make sure to have a 2 in front of the Na, so you get Na2SO4 plus H2. Al again will push out the hydrogen, so make sure to put a 3 here, so you get AlBr3. Oops, wait. 2Al plus let's see here, AlBr3 plus H2, right? So you need like a 6 here, so you'll get 2 AlBr3, okay? So 2 AlBr3, so 2Al plus 6 HBr gives you 2 AlBr3 and 3 H2, okay? Okay, how do you balance these acid-base reactions? For me, the best way is to balance the water, the net reaction, all right? Then the rest comes in easy. So you need a 2 here because if you have 2 OHs, you need 2 H's. So you'll get 2 waters, okay? So once you have that, then it's easy to put the other 2 together, then MgNO3 2, okay? Okay, so writing the balanced equation for MgOH2 plus HBr. So if you have 2 OHs, remember you need 2 H's, so you get 2 waters, and then what's left is MgBr2. Okay, it says select the correct group coefficients for each of the following neutralization reactions. Okay, so you have a 3 OH, so you need a 3 here. Okay, so that would balance it out. Okay, so you'll 3 here, this is fine, and then a 3 here. Okay, so 3H and 3OH will give you 3 waters. All right, so 3, 1, 1, 3, and that would be C. Okay, so if you have 2 OHs and 3 H's. The common denominator is 6. So you need a 3 here. That'll give you 6 OHs. And then you need a 2 here. That'll give you 6 H's. So that'll give you 6 waters. So 3, 2, 1, and 6. 3, 2, 1, and 6. So that would be B. Antacids are usually either hydroxides, but a lot of the times it's bicarbonates and carbonates as well, all right? So they have to neutralize all that excess stomach acid sometimes when you have indigestion, all right? So these are usually they use things which are insoluble, like aluminum hydroxide or calcium hydroxide, because that way it won't damage the lining of the intestines and the stomach. Okay, right. So you see here carbonates which are harmless, or hydroxides which are not very soluble in water. 11.8 is acid-base titration. So in the lab, it's very common to do this experiment. You are given an acid of unknown concentration, okay? So you take a certain volume, maybe 10 ml of it, add some water in order to create volume, and then you fill up a burette with a base of known concentration, all right? So say you have the acid in here in the flask, in the volumetric flask of unknown concentration, all right? The base, which is sodium hydroxide, is say 0.1 molar, all right? So you fill up that the burette up to its 50 ml mark, and then to this acid here in the flask you add an indicator like phenolphthalein. And so the reason is that you want to see that when the acid is neutralized by the base, you can visually see that, all right, the end point or the neutralization point. All right, at the neutralization point, all the acid and the base, they're neutralized. That means you get salt and water, okay? So you add the base drop by drop while you're stirring it or swirling it, and then wait for that color reaction, okay? At a certain volume, after you've drop by drop let down the base to neutralize the acid, you will see that there'll be a pink color. So phenolphthalein is pink in base, all right? So just a little drop of the base and you see the pink color, which indicates the end, or the fact that the acid has been completely neutralized by this base. Then you can go about calculating the molarity or the concentration of the acid. Okay, so you have used a certain measured volume of an acid. You have also know the volume of base required to neutralize that measured volume of acid, all right? So then you'll take the concentration of the base and the volume used, find out the moles of base, use the mole factors to convert it into moles of acid, and then divide it by the volume of acid to find its molarity. Okay, so you're using a specific volume of acid, say the 10 ml that I said, all right, and then you're going to see what that volume of base is that was able to neutralize that. Okay, the indicator tells you when that end point or the neutralization point is reached. Okay, so the end point is when the mole of the base is exactly equal to the mole of the acid. Okay, so then you're going to use that volume of the base, multiply it by the molarity of the base to get the moles of base, convert it into moles of acid, and then take the moles of acid, divide it by its volume to get its molarity. All right, what's the molarity of HCl? If 18.5 ml of 0.225 m NaOH is required to neutralize 0.01 liters of HCl. Okay. All right, now you can use M1V1 here. Okay, so 18.5 times 0.225 is equal to 0.01. Okay, so 18.5 times 0.225 divided by 0.01 will give you the molarity of HCl. Okay. All right, you can do it this way, or you can save time by using M1V1. Okay, so here's a shortcut. So use M1V1 or MAVA is equal to MBVB, where A is acid or B is base. Okay, so at neutralization, moles of acid must equal moles of base. Okay, if you're using acids which are not, so you would use this MAVA formula. Okay, if the acid is monoprotic and the base is monobasic, that means the acids have one proton. All the acids used in the reaction, neutralization reaction, have one proton, and the bases used in that particular reaction have one OH. Okay, so if there's only one OH in the base or one H plus in the acid, then use MAVA is equal to MBVB. But if you're using an acid like sulfuric acid, which is diprotic, or H3PO4 triprotic, or the base could be monobasic or it could be dibasic like MgOH2 or CaOH2, then an expanded form of that formula is NaMaVa is equal to NbMbVb. Okay, so Na is the number of H in the formula of acid. Okay, so for example, H2SO4, Na is going to be 2 because there's 2 H's in H2SO4. Nb is the number of OH in the formula of base. So AlOH3, right? There is 3 OHs. So Nb is equal to 3. Okay, so you don't have to even bother to balance the reaction. You can just use the formulas and do this. Okay, Ma molarity of acid, Va volume of acid, Mb molarity of base, Vb is the volume of base. So then just go about using the numbers given and plug and chug. Okay, so that reaction that I talked about, 25.5 ml of 0.438 molar NaOH is required to neutralize 0.0250 liters of HCl. So using the MAVA is equal to MBVB. Okay, Ma times the 25 mil, you can convert everything into mil, is equal to 0.438 m times 25.5 mil for the base. Okay, then divide both sides by the 25. So Ma works out to be 0.447 molar. Or you can do it the long way and you'll arrive at the exact same answer. Alright, so try out this NaMaVa is equal to NbMbVb for these particular problems and see how they work out. Okay. Alright, we'll stop here.